We probably should start our activity print seminar, and we're happy to have Peter Koroteev today, who will speak about 1D statistical mechanics with implementation of Resurgence. So, please.
Thank you. Thank you very much. Hi, everyone. It's great to be here. And then if you look at the dates for this papers came out, my talk is just more suited for literature seminar than for research. Like, as some of you know, I moved to math now, but these are all results, which I'll explain to you, and I hope it can facilitate some discussion. So, yeah. Let's get started. It's probably not going to be a typical string theory seminar, although, well, we'll see. Okay. Now this is not working either. I need to activate the. Yeah, there you go. Thanks. So the first half of the talk, well, maybe 60% or so, we'll be talking. Let's talk about biology, biophysics, right? So in cell membranes, there are those opening channels, right, that allows ions to go through. For example, when the cell is exchanging material with the environment or with other cells. And then, so nature is very smart, and it builds those channels using laws of physics, but such that whenever it can only get things in and out only when it wants to, right? And the first story that I'm going to tell you, it's motivated by that. So this is how it looks like in the electron microscope. So there is certain kind of protein which is wedged inside the lipid wall, right? So these are kind of fatty kind of acid things which are connected together. And the channel is very narrow. It's maybe like 5-6 angstrom in diameter. So, there was a Nobel Prize awarded about 20 years ago in chemistry to these two gentlemen for a discovery of water channels in cellular membranes, right? So that's how it would look like in their model. And so the physics of it is the following. So the water famously has a high dielectric constant, right? So like about 80 as compared to, say, the fatty acid, this lipid, which is a cellular membrane. And then if you have an electric charge, so assume that these are ions which are charged either positively or negatively, then the electric field will spread out, in the symmetrically, but because there's a big difference between those epsilons, most of it will stay inside the channel, right? So the way boundary conditions of Maxwell equations work is that essentially all the fields, like it prevents the electric field to escape the channel, right? So you can calculate the effective length. So like if so you need to take the root of the ratio of those electric constants, and then it would be of the order of the magnitude of the length of the channel. So typically, this membrane has 120 angstrom in size, and the channel is very narrow, like the width is very small. So with a very good approximation, we can think of channel here as to be in one-dimensional. So electric field is one-dimensional, and we can use laws of electrostatics, electrodynamics in one dimension, which are relatively simple. So here's another joke about spherical cows. Now I'm going to do cylindrical cow. So because of what I just said, we should think of electric field, so it's trapped inside this channel, right? If we have some number of charges inside this thing, the total value of electric field is quantized in this units, right? So 2 times the electron charge divided by the radius squared times epsilon of water, and then because it's a one-dimensional Coulomb system, right? So the solutions of Laplace equation in one dimension is the linear potential, right? So the farther the charge, the stronger is the interaction. And then if you calculate the energy, like so, you put some charges in the channel, and then you calculate how much energy it would take to take a probe charge and pass it through the channel. Turns out that if you plug the numbers in, it's actually quite large in relative units. So it will be 4 times the Boltzmann constant times the room temperature, and that's typically too much. So like the cell wouldn't be able to conduct its functions, right? So we need to somehow lower this barrier. The threshold for electric transport should be lower than that, right? And nature, of course, is smart. It solves it by screening. There is a screening target, right? So that's where green charges one conformal field theory came from, right? So at least the motivation. But yeah, so you would have ions of different charges, positive and negative, and of course, when they're next to each other, the electric field will get compensated, right? Yeah, and then well, we'll see you later in the talk, but so if you screen it properly, then the energy level, the barrier drops to by a factor of 4. So it's about Boltzmann constant times room temperature, and that's enough. That's enough to pass the ion. So what I want to tell you about is to describe statistical mechanics of this one-dimensional Bohm systems and see how it connects to other things that we know. Now, so what's the since it's a problem with two boundaries, there's a left boundary and a right boundary. So there's an optional boundary charge, right? And then it will define modular QE0, right? So because you see so you can have this trivial boundary condition whether it's 0, 0 here, 0 here, or like you can have E half, negative E half, or E over there, depending on exact distribution of charges, right? So you should think of it this way. So charges, the electric charges was quantized, but the boundary values are the boundary charge is continuous, right? It's a continuous parameter that varies between 0 and some value, right? So it will somewhat look like right angle as we see it. All right.
Just alpha.
Alpha is the concentration of ions. Yeah. So with the higher the concentration, so it there's an exponential damping of the energy of the barrier with the concentration of ions. But the more positive negative pairs it would be, stronger the exponential suppression of the potential. Okay, so now let's rewrite it in some more familiar terms of quantum field theory. So let's sigma j will be those charges, right? So those are ions of charges, either plus n1 epsilon or negative n2 epsilon. So let's assume for simplicity that there are only two, say, n1 is 1 and n2 is -1, or maybe 2 and -1 and something like this. And then we'll write the grand canonical partition function, right? So here, F1 and F2 are fugacities for each of type of ions, right? And then we would take a sum over this grand canonical value of all possible, and one goes from 0 to infinity, right? And then so we'll integrate this over or twice over the length of the channel, and we integrate in this exponential, right? So exponential minus the potential energy times divided by Boltzmann constant. Yeah, it was a condensed matter paper, so to write Boltzmann constant, we didn't put it to 1. Okay. Now, and then there's a standard trick which is used in statistical mechanics. And I'm sure somebody is giving a lecture course in PIMSA on that somewhere. So we can rewrite the grand canonical partition function as the quantum mechanical amplitude, right? So when I rewrite it as a path integral, right? So path integral with some Hamiltonian. So it's been done many times in various examples. So let's do it here. So let's introduce the charge density function, rho, and then because these are point charges, right? So they allocated to some positions x sub j, and then so it's a delta function, a sort of delta functional distribution multiplied by values of those charges, right? And then the first trick is to rewrite the delta function as the path integral, right? So where theta of x is the auxiliary field, which will become important in a second. So we want to rewrite our quantum mechanics as, so our partition function as a quantum mechanical amplitude, where this theta guy will be the coordinate, right? So it's kind of emergent degree of freedom, which will which appear in the quantum mechanical construct. So yeah, and then, so it's all pretty standard. So you can resum those x integrals. So you would do Yeah, so if you do this, well, we can do each of the integrals separately, right? Because of the delta function thing. Yeah, and then you have to see it will be like it's like a double exponential here. So there's a sum over n f integral of this thing to the n divided by n factorial, right? And then it will be exponential of the exponent. And then another standard thing would be because well, because of the Laplace equation, right? So the density satisfies the Laplace equation, we can well, integrate over x now, right? So because so this is the so that was integral over x's, x1 and all of those x's, and integrals all those x's they factorize, and then we do the path integral over x's, and that would result in inverting the Laplace operator. And so that's why there's in the integral you will have nabla over here, right? So the integral exponential integral dx stated this to this way. If you haven't done this, it's a exercise worth doing. Okay, and then after after the dust settles, this partition function becomes an amplitude, right? So from a state which is labeled by charge density q, all to itself, and then this x stands for space ordering, so ordering along the length of the channel. So it's x ordering, exponential, and then so you have an integral over of x over certain Hamiltonian, which I'll show you in the next slide, which looks like this, right? So again, well, according to Feynman rules, we can think of a partition function as an amplitude, right? And this amplitude we can rewrite as a sum over, so if E sub m, if ket m, right, is the state, right, is the eigenvalue, eigenfunction of the Hamiltonian, we can rewrite the amplitude, we can rewrite the partition function as a sum over the spectrum like this. So these are kind of overlaps between the boundary state and each of those states in the spectrum. Square absolutely squared times the exponential. So and what's important is that this Hamiltonian looks like this, right? So now theta becomes the new coordinate, that auxiliary field that's introduced by hand. And then it's shifted by q. So q looks like a theta angle. In quantum mechanics, you can also think of theta angle. And this is the potential, right? So potential is so it's a sum of two exponentials, complex exponential. So alpha 1 and alpha 2 are integers. So these are alpha 1 is the concentration of ions of charge on 1. Alpha 2 is concentration of ions of charge negative and 2. Yeah. And yeah, so this is how they're related to fugacities.
It should be turning, it's not a mixture.
Very good. Yes. So it's not CPT symmetric, but it will be PP symmetric. And that will do for us. Yeah. So Serge is making the right comment in it. So the fact that only unless n1 is equal to n2, right? But if they're different, it's not going to be written. But that's okay because its eigenvalues will be located either on the real line or symmetric relative in a complex plane relative to the real line. Technical questions. Yeah, so if you want, you can read about this in the paper, but yes, but like I think it was Polyakov who invented this trick, right? So you write in statistical like grand canonical function in the quantum mechanical amplitude. Yeah, but all classical without. Good. So and then so those functions they are periodic in data, right? Because remember, I remind you, state is a periodic coordinate here, right? So we should think of state as being something real. So it's a periodic thing. So wave functions must be 2-pi periodic in our normalization, and this is the scalar product in the Hilbert space of those states. Good. Now, and then as I mentioned, the boundary charge plays the role of this block quasi-momentum, quasi because it's defined modular the value which is determined by the flux, electric flux coming from one charge, which I call P0. Yeah, and then you can see that this looks like a Fourier transform. And so, so where Q is like momentum or quasi-momentum, so momentum is periodic, because the integral values of charge can be screened by other ions, right? Basically, if you add another charge, you only worry another ion. You only worry about the string modular to modular the value of the flux. So now, well, we can compute various thermodynamical properties. Like one of them will be the pressure, right? So the way you do it, you would take the ground state energy, right? Take a derivative with respect to the volume, right, which is one-dimensional in this case, and send the size to infinity. You're gonna get this thing, right? So it's the ground state energy, E0 of Q, right? And then to the energy barrier for the transport, right, of those charges, it will be proportional to the width, what is called of the first block band. So this delta zero, which we'll calculate in a moment, right? So that's exactly the value that we're trying to understand how like the screening of charges allows us to make it as small as possible. Okay. So the transfer properties will depend on these four variables: the ground state energy, the width of the first block band, and then the charges of the ions. And then we'll find all these using semi-classical methods, which we used to quite a lot. Okay, so let's talk about symmetries. So yeah, this is the original paper, right? So so it's a condensed matter paper. That's why authors are written from youngest to oldest, although there will be some anomaly in that. Anyhow, so this is a Hamiltonian, right? And so instead of CPT symmetry, we only have PT symmetry. So P, which is the sign of theta, and T is the complex conjugation, right? And you can see that it's PT symmetry. So if you do this at the same time, you're gonna have this symmetry. And another one is the shift symmetry. It's called isospectrality. So this combination here is constant, right? And you can use it to scale the whole formula. So if you do that, you'll get this. So there's like an alpha, which is kind of the normalized concentration multiplied by the P squared and plus this potential. Okay, now, and then the way quantization works is quite peculiar. So the P operator, P hat, is the derivative shifted by Q, right? Times square root alpha. And then if you calculate the commutator, you're going to get I alpha is -1/2. And if you, well, remember what should spend in right hand side in quantum mechanics. So it's a Planck constant, right? So it kind of in this formula is the concentration as the meaning of the Planck constant. So for my friends from integrable systems group, here's another quantum classical duality. Okay. You want to split more? Yeah. So that's right. Now,
so semi-classical means low density.
Large action.
Yes.
Large action, like action functional. Right? So right. So typically, like the.
Sending the Planck constant to 0, which means concentration to 0 to be the classical ring.
Oh yeah, that's another way. Yeah. So yeah,
that is.
Yeah. So
when we deal with Planck, all means classical.
That's right. That's right.
That's precision. We just say that concentration plays the role of the Planck constant, which you can send to the possible.
That's correct. Yeah, that's. Yeah. So well, in fact, yeah, in the following slides we'll look at both classical regime and strong coupling regime. Where, so yes, strong coupling would be large alpha. So yeah. Now numerically, it's really easy to do. It's like we can take high school students or whoever and just ask him or her to do mathematical code in like 10 minutes. So you can take a Fourier transform of the Hamiltonian, right? And then so it becomes the matrix. It's infinite matrix, but you can just truncate it as say 20 or 10, and you'll be surprised how quickly the numeric saturates. So because this example is given for n1 equals 2, I think. So that's why I have like you have the diagonal, right, coming from the squared term, and then you have the two diagonals above it, right? And then you have one diagonal that was sub-diagonal. This is called super diagonal, and I don't think there's a name for the next one. Yeah, so you take this matrix, right? So clearly it's not Hermitian, but that's okay. So Q takes values in the unit interval, and you can just, diagonalize it on the computer. I just ask to diagonalize the matrix, and this is what we're going to get. So let's normalize the energy into this variable which I call U, right? And I'm going to draw spectrum on the U plane. Now, color here means the value of the quasi-momentum. So I forgot which one is which, but yeah, interpolating between blue and red corresponds to kind of moving through the range of the quasi-momentum, right? So that's on negative half to half. And then you can see that so this is 2-1 guesses, right? So N1 is equal to 2 and N2 is equal to -1. So here you see that so there's different behavior of those bands in like there's something interesting going on inside the unit circle in U and outside of the unit circle in U, depending on the concentration. Yeah, so this is like weak coupling, semi-classical, and then like alpha equals 200 is strong coupling. So you can see that what happens at strong coupling, there's those asymptotes here. And then the number of those rays that emerge from point U equals 1, right, is determined by it's essentially a floor of square root lambda, right? So in this case, square root alpha. So depending on the charges of your ions, right, you can have different number of those branches, those arrows that come in it. So outside of the unit circle bands are wide, right? So you see it kind of changes over the large range, right? So as we vary the quasi-momentum, and inside they're narrow, right? So while alpha equals 2, they look kind of shortish, right? But yeah, so it's still symmetric with respect to the Lie system. So yeah, so like now, question to my string theory friends: letter U reminds me of which theory? Which solution? SU, but yeah, where we use letter U? Cyberquitting, that's right. So it's in part will be inspired by cyberquitting. So we can think of this as a cyberquitting plane. Okay. So a little bit more details about the band structure. So if you take alpha equals 1, right? So and you can draw the band structure as function of quasi-momentum. So there'll be real bands, right? And complex bands. So the complex one is shown in dashed line. So here, those which go into the complex plane above and below, right? So that's how that's kind of a typical structure of the spectrum here. Okay. Yeah, and then interpolation between different couplings. So strong coupling with alpha here, right? So here you have strong coupling for different charges, right? So different charges of ions. For T1 gas, so we have 3, right? So for 3-1 we also have 3, but then it kind of jumps, right? So for 4-1 we have 5, and for 3-2 we also. It's kind of hard to see, but it's supposed to be like extra branch over here. So same thing here, right? So and you will see soon that this will be related to the genus of the Riemann surface that underlies this geometry. Good. Yeah, and then you can even like a strong coupling you can solve it analytically, but it's relatively easy to find the like the angles at which those branches emanate from the equal 1 point. Okay, now let's talk about so that was numerics. Now let's talk about analytic solution. So it's as amazing as the numeric solution. So first let's consider the emission case, and 1 equals N2 equals 1. Then the potential is the cosine function, right? So we have this energy equation, right? So now the action form, or holomorphic differential looks like P theta, right? So there's a holomorphic, there's a symplectic form that we can write. Or using this exponential change of variables, we can rewrite it as so, right? So 2u equals p squared minus z plus 1 of p squared. And of course, those work in supersymmetric Gibbs theories immediately realize cyberquitting curve, right? So for which theory? Which theory is that? Come on. Which cyber-equipment solution is this? SU2, pure SU2, right? So U is trace phi squared, right? Classically, and yeah, so so this is the simplest one. It's the first paper by Saber-Quitten in '94. Now, yeah, so the way we approach this analytically is that we think of this as a equation for the double cover of the z-plane, right? So you will have so you will have what two so there'll be three critical points where t squared equals 0, right? So three branching points, and there'll be one branching point at infinity. So one is at z equals 0, and then there'll be two pairs of points z plus and z minus, right? And then we should think of this as not a complex plane, but a Riemann sphere. So that's why you add infinity. I'm sure most of you have seen this, so just in case. And the way you see the torus, so like the curve here, is that you would kind of tear off those cuts, right? And then you would take two copies of them because it's a double cover, and then you would connect these two Riemann spheres along those cuts, and you'll get a Riemann sponsor, right? So the mass spectrum of the theory, as well as the Saber-Quitten case, comes from integrals of the Stelmach differential over the A cycle and B cycle of torus. So in terms of particle in this cosine potential, it means the following, right? So P is the momentum, U is the energy, right? And then theta is the coordinate. So yeah, this is a sine function, like it goes to infinity, right? And as we know from quantum mechanics, there are two types of trajectories. So one is a classical Laurent trajectory. So your particle kind of, at a given energy, bounces back and forth in potential, but there are also tunneling processes, right? So it can tunnel through the next minimum, and then it can tunnel through the next and the next and the next. There are instantons. There are quantum mechanical instantons. And then, one of the period integrals will be related to classical trajectory. That one will be related to instantons, right? And it's clear what's going on. So around z equals 0. So remind you, z is exponential to the I theta. So p behaves as a negative square root of z, and z infinity behaves like that. So it's kind of when we can relate to which regime it corresponds to. So now so we should think of as a torus vibration over the u-plane. Like I said, we'll compute those period integrals, and then there will be 3 points in u-plane where something special going on, right, with those cycles. So at u equals 1, right, the one of the cycles shrinks, goes to 0. So I call it delta 1 here. At u equals -1, the other one shrinks. Right, so you can figure out which one goes where. See, so z plus minus goes negative u plus minus square root, right? And then if u becomes 1 or -1, it vanishes. So these 2 points coincide, and it means that the two branching points collide, right? So in the period integral vanishes, right? You can contract it to a point. So there's 1, -1. Okay, another trivial question. What's the third point? No, not 0 and z, but in u. So in u, you have 1, you have my -1. What's the third point? So this is monopole, this is diamond, but what's the classical? That's right. So classical is infinity. Now let's let me not refer to Saber-Quitten too much, but yeah. So let's talk about particle and the potential. So what does infinite energy mean? It means that the particle is far up there, right? So it doesn't feel the difference. Like if it kind of flies over here, there'll be this over barrier scattering, right? And it will be some bands and gaps. Whereas if it goes really far, then it doesn't feel anything. And so just different linear combination of cycle strings. It's something like delta 1 minus delta 0 equals 0. Like that. Okay, very good. Okay, so you've seen all that. Okay, so now a little bit more, again, it's in slightly different papers or follow-ups. So we can think of it as a, so how can we approach these different solutions? So those period integrals, they satisfy what is called Picard-Fuchs equation. Right? So what does it say? So in this case, the torus, the James one surface, it has two-dimensional homology. Its first homology is two-dimensional, so there are two two independent forms that you can write lambda and lambda prime, right? And you can well, period integrals. So you can write a degree 2 equation, differential equation, which would such that period integrals of lambda and lambda prime will be solutions of that equation. And so the way to derive this equation in practice is the following. So you need to, well, so take the holomorphic form, right? Meromorphic, and then you need to, well, you can essentially guess or find the operator, the differential operator that acting on that thing gives you a total derivative, right? And then as you integrate the total derivative, you're going to get 0, right? And you'll get yourself the Picard-Fuchs operator. So in this example, this is the Picard-Fuchs operator, the Picard-Fuchs differential equation. This equation has 3 regular singularities, same ones that we discussed, right? So plus minus 1 and it's empty, obviously. And it has 2 solutions, right? And they are known special functions. Right, so the hypergeometric function with different values of parameters. Right. Yeah. So now and then so this is the solution. This is the space of solutions. Now we need to identify the constant by relating them to the boundary conditions, right? So say there's S0, the period integral around the A cycle, there's the period integral around the B cycle, right? And these are the linear combinations. And then just by looking at the boundary conditions and the potential, you can infer that these 4 coefficients, of course, are not unrelated. You can evaluate what they are by simple calculation. And then you'll see the following, that so near U equals -1, the ion point, right? In Statistical slang, S0 will be linear, so it will vanish linearly, but S1 will have a logarithmic prime spread, right? And that's why there will be a monodromy, non-trivial monodromy around this point, which you can calculate. So let's call this matrix M-1, right? So this is it's the monodromy matrix on the solutions of the Picard-Fuchs equation. So we can sort of characterize each singularity with its monodromy matrix. Okay, and then sort of first kind of implication of resurgence is that, well, essentially there's a the classical solution, right? So it's remember this picture from before. Right, so think of this as related to the S0, and this is related to S1. Right, so there's a analytic relationship between the classical solution and the classical solution and the Stanley solution over there, right? So the instant that goes through the potential. Okay, so let's talk about monodromies a bit more. So near U equals -1, this is the monodromy. Then near U equals 1, you can do the same exercise. This will be the monodromy. And then the classical regime, you can just solve it by hand, right? And then with a little bit of work, you can show that this is the monodromy around infinity, right? Around point infinity. And you can check that the total monodromy is trivial. So like infinity monodromy is the product of these two, whichever way you define it. You can invert this matrix, put to the right hand side. Okay. Now let's talk about spectrum. Finally, so we have this analytic structure. Now let's look at this bands and gaps that we wanted for our one-dimensional channel. So the WTB quantization, right, looks as follows: near U equals -1. So again, so U equals -1. In our case, corresponds to right, to the classical minimum. Yes, we have this, and we have this factor 1/2. right? And then the energy levels. So remember, these are just the rescale. This is just the rescale value of the energy. Now, well, we can compute the pressure as the derivative of the well. After computing energy, you can see that it consists of two parts, and then it nicely reproduces classical results from condensed matter literature. So this contribution is called it comes from mean field theory approach, just MFT, and this is the one we're correcting. It's called Dubai heat. Then to find the bandwidth, we need to evaluate the instant on action. So it's that the timeline trajectory in the graph, right? So the delta U, the bandwidth, right, is given by the e to the instant on action, right? And then again, simple calculation shows that it should be equal. So if the value of the action is equal to this from the analysis that we just did, and then the bandwidth is equal to, well, this formula, give to take it. And if you open the old textbook and Mathieu equation, that's exactly what they have for the gap. Any questions?
What's the Mathieu's equation? Equation.
Just writing your equation, cosine potential. It's one of those classical equations in mathematical physics that people talk about a lot, and here essentially get this, well, this part of the spectrum for free. And you can keep going. So this is the like instant on amp, instant on pair. So the way this formula is obtained is like you would calculate like instant on action. It kind of goes this way and that way, right? And then it's like twice the kind of tunneling amplitude, right? But then you can add more. You can add next guy and the next one and the next one. You can have in a sector with total number of 0 instant on, right? There are several instant on anti-instant on pairs, and you can compute corrections. Yes, in fact, if you do it, so these two gentlemen, they're really kind of efficient and doing and drawing this, right? So this plot essentially means that the Planck's constant is alpha in my case, so gray areas are disallowed regions, right? Where the particle cannot be, and then whites are where you can find the spectrum. So so -1, is this like normalized heights of the cosine potential, right? And then as you once you below below 1, pretty much everything is allowed, except once you start coming up, there will be certain kind of over-barrier scattering, which prevents you from happening. And then you go all the way up, then you'll have just only discrete levels, because it's like having a particle in theory potential, right? So you only have like the discrete values, like if you really find the energy. Okay, now let's do let's do another example. Let's do 3-1 gas. So I'm going to do it really quickly. So now again, this equation gives us a double cover of complex Riemann sphere with how many? 6 branching points, and you connect them with 3 branch paths, and you get a genus 2 circle, right? And then the corresponding Picard-Fuchs equation has degree 4, right? And it has 4 independent cycles, 4 independent solutions. And again, well, you can match the analytic equation with the WKB results near U equals -1. This is great results. Well, great, I'm sure great. So this is a strong coupling thing, right? So yeah. And then in this case, instant on is a certain combination of this actions over here. Right, so like these are classical. So these are values when the classical action is real, and these are the points in the spectrum when instant on action is real. And then you can do it for any coprime N and M, the charges of ions, right? You can play with the differential equations, and well, it sort of flies those, yeah. And then well, essentially see that same as with the genius of the elliptic curve, right? It jumps every two, right? So if you have double cover, ramified cover of the plane with 4 branching points and 3 branching points, it's in genus 1. If you have 5 and 6 is genus 2, if you have 7 and 8 is genus 4, genus 3, and so on. Yeah. So, but each of those cases will exhibit this behavior when around each of the around a singularity action would scale as square root of u, the one of the actions, and then the other one will be will have a logarithmic branch cut. Okay, so I'm going to switch gears. This is the second part of the talk. We're just going to talk about resurgence in general, and then yes, I hope that question. Let's stop here.
Quickly recap in this general done also.
Yeah.
What effect you can recap implies that you have this multiple instant of contributions that you can resum, or
that's right. Yeah.
and those white regions, like you said, the ones
in the white. Let's see, remember. So I think so. Those branches are where you can find the spectrum, and the grays ones are where which are forbidden.
Yeah. Right.
Yes. Okay. So classically you have this WQB states, right? And then kind of above we have, well, if you have a large energy, it looks like it's a particle in periodic potential, right? It has this on the.
Well, yeah.
Good. Okay. So let's talk about a little bit about resurgence, and then we can adjourn. So in a nutshell, well, yeah. So one can give a math talk about resurgence. So there's a beautiful work by Resurgence and Subliman. They've been working on this for years, and part 1 is out, and then they're working on part 2 and part 3. So they call it homological Flory theory. So maybe I'll give a talk in a math seminar about this sometime later. But let me just apply kind of to physics. Let me emphasize on physics part of this. So in a nutshell, it's resurgence is about connection between perturbative and non-perturbative phenomena, right? So if you look at quantities of the computer quantum field theory, like partition functions and correlators, at their analytical structure, so how they depend on the coupling constant and all other parameters, and what are the connections there. So we have seen a manifestation of resurgence in the first part, right? So the instanton action and the classical action were related by some kind of analytic continuation like that. So I think this is literally true if you just take, I think, like at 0, like at half. You take at this level, so the values are the same, right? And then you just need to space in some phase there. Now, so and as we discussed before, so this action with no instantons is very related to the action with a instanton anti-instanton trajectory. So that's how you have the correction to the bandwidth, and then you can have 2 instantons, 2 anti-instantons, and so on. So there'll be entire tower. So you can have those things, and then all of them are connected to each other via this resurgence, right? And so part of the reason why it's happening is because the perturbation series in quantum field theory is generally asymptotic, right? So it's very badly behaved if you take it as a face value. Let's do just that. So let's just do a very naive thing. Take a very simple integral. It's like 0 plus 0 dimensional example, right? We're just going to take this integral. So again, we take a trigonometric function, sine squared, which is the same as cosine, right, after some shifts. So G is the coupling constant, integral from negative pi half to pi half of this function. Okay? Now, well, I mean, you can ask your computer to do it for you. It's going to be Bessel function. Now, let's think about this as a quantum field theory. So it has two saddles, right? 2 critical points. One, the perturbative one at x equals 0, where action vanishes, right? Because we need to, when we do the minimal action principle, right? We actually do an extremal action principle, right? So there'll be a minimum and there'll be a maximum. So this will be the minimum, this will be the maximum, right? So S will be equal to 1/2 G at x equals pi half. Now, if we do the perturbative expansion, you can just, again, ask your computer to do it, and you see that it's not looking good, right? So just by how many digits you have in the numerator and the denominator, it's clearly badly divergent. right? In fact, it's factorially divergent. And then, in asymptotic analysis, there are these resummation techniques like Borel resummation and others. So I'm not going to emphasize those. Instead, we'll do something else. So you can resum, but let's try to, entangle this mass in a different way. So if you want to find a well-behaved answer, kind of nicely behaved answer, like something convergent, then we should take, we should, like the partition function should be some kind of doubles, like series in, from contributions coming from perturbative saddle and from non-perturbative saddle. So sigma 0 and sigma 1 are some kind of constants. Later you can prove that they must be integers, right? And p's are some other case you can prove here. Now, and then let's rewrite this integral slightly more welcoming form. So do some rescalings. So Z inverse is G, and then so you're gonna absorb some factors here, and then so if this is Z star, then Z is the original partition function is Z star up to this P factor. Well, and now let's guess the Picard-Hooke's equation, right? So let's guess the second order differential equation that this guy satisfies. Well, and before we do this, let's do another change of variables. So if we get rid of trigonometric functions by this substitution, then you're going to get, there's exponential, and in the numerator we have square root. And that suggests there's some branching going on, right? So along the lines that we saw already. And let's just keep the contour of integration free. So now we lift everything, become complex, x is complex, phi is complex, everything is complex, because that will allow us to do the computation. So, and now we want to interpret this as a period integral of this differential, over something, right? So let's try to understand the topology of this, something that this differential is on. So there must be some kind of bit, so we'll call it a cycle, whatever that means, right? So say integral from negative pi to pi, let's call it half a cycle, right? And then the b cycle will be found by solving the Picard-Hooke's equation. So you can just check that if you apply this differential operator, c second derivative plus first derivative minus c, on that integrand, you'll get a total derivative, right? So therefore, if you integrate it by over the closed path, you're going to get 0. This is the differential equation. It has two solutions, right? So when there's I0, there's also K0. Now the Bessel function. And then if you look at the expansion, so we've seen this results before, I0 is holomorphic, right? So it behaves like that. And K0 has a logarithmic branch that.
Sorry, that's just a precision. Like, so is there a deep reason why you say like integrating over, say, some manifold, and then you say let's try to get why the super?
I mean, so if you think of this hard enough, it will be some kind of degenerate torus. So, so this is the so what is Picard-Hooke?
Just not like Picard-Hooke should capture.
That's what it does, right? So if you have there's a family of period integrals, right? And they're related by, they are solutions for the Picard-Hooke's equation.
Yeah, but this you say this is something generic, right? Arbitrary genus or whatever the generic, right? So
I mean, why do you expect degree 2 equation, or?
No, like Picard-Hooke you're saying would capture this correctly, everything.
Well, I mean, as we saw, monoderm of Picard-Hooke's equations will capture this data, and that's really enough.
That's
right?
enough.
Yeah, that's enough. Well, it's enough for some fun. Right. So yeah, in fact, let's do just that. So if you do the half turn, right? So half monoderm here, you'll get K0 minus pi I0, and then you can define the A cycle integral as K and B cycle as I, right? Right, and then this way the partition function.
So you will capture both classes.
Yeah, okay. Yeah, so this is absolutely beautiful. Unfortunately, it doesn't work as easily for real life examples, but yeah. So the monoderm at 0 at origin is this. So it does the following thing with the period integrals. So that's essentially so perturbation theory is divergent. However, if you take the series and then subtract from it the same series after doing the monodromy for the coefficients, then you get the finite answer. And that's in a sense what Borel summation is doing, right? So you would, but there kind of you impose it by hand. You can just, okay, let's just divide all coefficients by 3 factorial and see what happens, right? And get the census justifies that. And I think I'm done. I think it.
Okay, question.
You quite get for different alpha I and we have you had a picture with different alphas and the number of arrays which are different. I think.
Yeah. Yeah.
I didn't get how we can get from the solution. How we solve these things in classically, how we can guess from the numbers you put here is the number of arrays, or if possible.
Let's see if I remember. No, it doesn't follow from the formula at all. It's so in a sense, well, I mean, it's related to the, but okay, the appearing pairs, right? So here we have this real array and then the pair of complex ones at this angle and pair of complex ones at that angle. There are 3 of them, and then one comes in the middle. So, and this is the genus resurgence. So each of them come from quantization of the period integral, like a cycle period integral. So the number of branches, well, what's the number? So number of branches plus 1 divided by 2 is the genus of the circle. And then it's the same thing.
Okay, more questions. Okay, maybe another question. In such systems, do you see or can you see any normal ones? Physical
Normal ones. I had. Can I see louder? The question was, can I see normal ones in any of my? First of all, I forgot what they are. I just remember, but
Interpretation corresponds to certain physical constants.
yeah, I don't know. I don't think that appears as, for example, you have to go with actual quantity behind it, like 1.0.
Okay. If there are no questions, then let's thank the speaker again.